Okay, hi everyone, and welcome back to Success 191. Today is a really exciting day because we'll learn about how we can actually marry two very long-standing fields in computer science and with reinforcement learning with recent advances in deep learning. And the topic of today's lecture will actually be on how we can combine those two fields and into the form of what's called deep reinforcement learning. Now, this field is really amazing to me because it moves away from this paradigm that we've been seeing in this class so far. And that paradigm is really where we have a machine learning model or a deep learning model that is trained on a fixed data set. Okay, so this is a fixed data set that we go out, we collect, we label, and then we train our model on that data set. And in RL, or reinforcement learning, the deep learning model is not going to be learning on some fixed data set that's static. Now our algorithm is going to be placed in some dynamic environment, and it's going to be able to explore and interact with that environment in different ways so that it can actually try out different actions and experiences so that it can learn how to best accomplish its task in that environment without any form of human supervision or fixed annotations from a human, or any form of human guidance, for example. All it has to define is simply some objective that the algorithm should try to optimize for. Now, this has huge obvious implications in many different fields, ranging from robotics to self-driving cars and robot manipulation, but also in this new and emerging field of gameplay and building strategies within games for solving and optimizing how an agent or how a player in the game can try to beat out other forms of human players. Now, you can even imagine a combination of robotics and gameplay now, where you train robots to play against humans in the real world. So here's actually an example that you may have already seen in the past about a DeepMind algorithm that was actually trained to play the game of StarCraft. And StarCraft, and the algorithm's name was AlphaStar. Now here you're seeing it competing against some of the top human players, and this was a huge endeavor by the algorithm creators, and this was a huge deal when this came out. And let's just watch this video for a little bit.
AI to be that good. Everything that we did was proper, it was calculated, and it was done well. I thought I'm learning something. Yes! It's much better than I expected it to be. I would consider myself a good player, right?
This is a professional player of StarCraft competing against the deep learning algorithm AlphaStar. And against this professional player who came in actually at the beginning of the video extremely confident that they would not only win, but kind of win convincingly, AlphaStar ended up defeating the human 5-0. Right? So this is really an extraordinary achievement, and we've kind of been keep seeing these type of achievements, especially in the field of gameplay and strategies. And I think the first thing I want to do as part of this lecture is kind of take a step back and introduce how reinforcement learning and how this algorithm that you saw on the last slide was trained in the context of everything else that we've learned in this course. So we've seen a bunch of different types of models so far in this course, and we've also seen several different types of training algorithms as well. But how does reinforcement learning compare to those algorithms? So in the beginning of this class, we saw what was called supervised learning. This is an example where we have a data set of X as our input, Y as our output, or our label for that input. And our goal here is to learn some functional mapping that goes from X to Y and predicts Y. Right? So for example, we could give a neural network this image of an apple, and the goal of our neural network is to label this image and say this thing is an apple. Right? So that's an example of a supervised learning problem. If we collect a bunch of images of apples, we can train that type of model in a supervised way. Now, in yesterday's lecture, we also uncovered a new type of learning algorithms called unsupervised learning. Now here, it's different than supervised learning because now we only have access to our data, X. There are no labels in unsupervised learning, and now our only goal is to uncover some underlying structure within our data. So here, for example, we can observe a bunch of different pictures of apples. We don't need to say that these are apples and maybe this other image is of oranges, right? So these are two different images. We don't need to give them labels. We can just give all of the images to our algorithm. And the goal of an unsupervised learning algorithm is simply to identify that, okay, this one picture of an apple is pretty similar to this other thing, right? It doesn't know that it's an apple, it just knows that these things share similar features to each other. And now in reinforcement learning, we are given only data in the form of what are called state-action pairs. States are the observations that an agent or a player sees, and actions are the behavior that that agent takes in those states. So the goal now of reinforcement learning is to learn how to maximize some metric of its rewards or future rewards over many different time steps into the future. So in this apple example now that we've been keeping on the bottom of the slide, we might now see that the agent doesn't know that this thing is an apple. And now it just learns that it should eat this thing because when it eats it, it gets to survive longer because it's a healthy food, right? This thing will help you keep you alive, right? It doesn't understand anything about what it is, or maybe even the fact that it's a food, right? But it just got this reward over time. By eating an apple, it was able to become healthier and stay alive longer. So it learns that that's kind of an action that it should take when it sees itself in a state presented with an apple. Now, RL, or reinforcement learning, this third panel is going to be the focus of our lecture today. So before we go any deeper, I want to really make sure that you understand all of the new terminology that is associated to the reinforcement learning field, because a lot of the terminology here is actually very intuitive, but it's a little bit different than what we've seen in the class so far. So I want to really walk through this step by step and make sure that all of it, from the foundation up, is really clear to everyone. So the first and most important aspect of a reinforcement learning system is going to be this agent here. We call an agent is anything that will take actions. For example, it could be a drone that's making a delivery, or it could be Super Mario navigating through a video game. The algorithm that you have is essentially your agent. So for example, in life, you are the agent, right? So you live life and you take some actions, so that makes you the agent. The next main component of the system is the environment. The environment is simply the world in which the agent exists and takes actions in, the place that it moves and lives. The agent can send commands to the environment in the form of actions, right? So it can take steps in the environment with actions. And here we can say that A is the set of all possible actions that this agent could take in this environment, capital A. And an action is almost very self-explanatory, but it should be noted that agents choose among a potentially discrete set of actions. So for example, in this case, we have an agent that can choose between moving forwards, backwards, left, or right. You could also imagine cases where it's not a fixed number of actions that an agent could take. Maybe it could be represented using some function, so it's a continuous action space. And we're going to talk about those types of problems as well in today's lecture, but just for simplicity, we can consider kind of a finite space of actions. Now, when the agent takes actions in an environment, its environment will send it back observations, right? So an observation is simply how an agent interacts with its environment. And you can see that it's sending back those observations in the form of what are called states. Now, a state is just a concrete and immediate situation that the agent finds itself in at this moment in time t, right? So it takes some action at t, it gets some state back at time t plus 1. And in addition to getting the state back, we also get what's called a reward back from our environment. Now, a reward is simply a feedback. Think of this as a number. It's a feedback by which we can measure the success of an agent's actions, right? So for example, in a video game, when Mario touches a coin, a gold coin, he wins points, right? Those are examples of rewards that are distributed to Mario when he touches that gold coin. Now, from any given state, an agent sends out or sends outputs in the form of actions to the environment, and then the environment will return in response with those states and those rewards. Now, if there are any rewards, there are also cases where rewards may be delayed, right? So you may not get your reward immediately. You may see the reward later on in the future, and these effectively will evaluate your agent's actions in a delayed state. Now let's dig into this reward part a little bit more now. We can also identify or kind of formulate the total reward that the agent is going to see, which is just the sum of all rewards that an agent gets after any certain time t. Okay, so here, for example, capital R of t is denoted as this total reward, or what's also called the return. And that can be expanded to look like this. So its reward at time t plus its reward at time t plus 1, and so on, all the way on to infinity, right? So this is kind of like the total reward that the agent is going to achieve from here on out. Now, it's often useful to not only consider the total reward, right, but the total sum of rewards, but also to think about what we call a discounted total reward, or a discounted sum of future rewards. Now here, the discount factor you can think of as this gamma parameter. So now instead of just adding up all of the rewards, we're going to multiply it by some discount factor, which is just a number that we can define. And that number is chosen to effectively dampen these rewards' effects on the agent's choices of an action. Now, why would we want to do this? So the discounting factor is effectively designed to make future rewards worth less than current rewards, right? So it enforces some form of short-term or greedy learning in the agent. And this is actually a very natural form of rewards that we can think about. So let's suppose I offered you, I can give you a reward of $5 for taking this class today, or a reward of $5 in 5 years from now, right? You still take the class today, but you're going to get the reward either today or in 5 years from today. Now, which reward would you prefer to take? They're both $5, right? But you would prefer the reward today because you actually have some internal discounting factor for those future rewards that make it less valuable for you. Now, the discount factor here is simply multiplied by future rewards as discovered by the agent as it moves through the environment, as it takes actions. And like I said, these effectively dampen the reward's effect on the agent's choice of action. Now, finally, there's a very important function in reinforcement learning, and this is going to be kind of the main part of the first half of today's lecture, where we look at this function called the Q function. Okay, and let's look at how we can actually define what the Q function is from what we've learned in the previous slides and all the terminology that we've built up thus far. Now, the Q function is simply a function that takes as input two things. It takes as input the current state that the robot is in, or sorry, that the agent is in, and the current action that it executes in this current state. Okay, so it's going to take as input the observation that the agent sees and the action that it's going to take in response to that observation. And the output of our Q function is going to return the expected total future sum of rewards that an agent can receive after that point, given that action that it took in this particular state, right? So if we took a really good action in this state, our Q function should return a very high expected total future reward. If we took a bad action, though, in this state, we should see that our Q function should reflect that and return a very poor or a penalized future reward, right? So now the question is, if we are given this, let's say, magical Q function, let's not say I am going to, let's say you don't care about how you get the Q function. Let's say I give it to you. So you're going to get some black box function that you can feed in two things to, the state and the action. And it's going to give you this expected future return on your rewards as a return. Now, how can we, let's say we are agents in this environment, how can we choose what action to take if we have access to this magical Q function, right? So let me ask this kind of question to all of you, and I hope maybe you can take a second to reflect on this. Let's say you're given this Q function. I'll just repeat the question again. You're given this function, it takes this input and kind of evaluates how good of an action this action is in your current state. How can you use that function to determine what is the best action? Well, ultimately, we want to kind of infer, we need to create a policy, let's call it pi. A policy is something that just takes as input the state. And that policy, the goal of the policy is to infer or output the best possible action that could be executed in this state. right? So think of a policy as just another function, takes as input your state and outputs what you should do in this state, right? So that's the ultimate goal. That's what we want to compute. We want to find what action do we take now that we're in this state. How can we use our Q function to create that policy function? Well, one strategy, and this strategy is exactly the correct strategy that you would take, is that you should just define your policy to choose the action that will maximize your Q function, right? That will maximize your future rewards. Well, how do you do that? Well, you have some, let's say, finite list or finite array of possible actions. You can feed each action into your Q function along with your current state. And each time you feed in an action, you're going to get like how good of an action was that from your Q function. That's what your Q function tells you. And we just want to find the maximum of all of those different future returns of rewards, right? So by finding the argmax, we identify the action that yielded the best or the greatest return on our future rewards as possible from this current state. So we can actually define our policy, our optimal policy at this time. We'll call pi star, which is denoting the optimal policy at this state, S, should just be the argmax, or the action that results in the maximum Q value at this time. Now, in this lecture, we're going to focus primarily on two forms of reinforcement learning algorithms that can broadly be disconnected into two different categories. One of which is where we try to actually learn this Q function and then use it in the exact way that I just described on the previous slide, right? So assuming we have the Q function, we can solve the problem of reinforcement learning just by using this argmax over our Q function. But then the question is, how do we get the Q function, right? Previously, I just said I'll give it to you magically. But in practice, you'll need to actually learn it, right? So how can we use reinforcement learning and deep learning to learn that Q function? That's going to define what we call a value learning algorithm. And the second class of algorithms are what we call policy learning algorithms, because they try to directly learn the policy that governs the agent and then sample actions from this policy, right? So you can think of almost policy learning as a much more direct way of modeling the problem. Instead of finding a Q function and then maximizing that Q function, you want to just directly find your policy function and use the neural network to optimize or identify your policy function from a bunch of data and then sample actions from that policy function. So first, let's look at value learning, and then we'll build up our intuition, and then we'll extend on in the second half of today's lecture onto policy learning. So let's start by digging deeper, firstly, into this Q function, since the Q function is actually the foundational basis of value learning. Now, the first thing I'll introduce is the Atari Breakout game, which you can see here on the left. The objective of this game is essentially that you have this paddle on the bottom. This paddle can move left or right. That's the agent. So the agent is the paddle. It can move either left or right at any moment in time. And you also have this ball that's coming at this moment, coming towards the agent. Now, the objective of the agent, the paddle, is to move in ways that it reflects the ball and can hit the ball back towards the top of the screen. And every time it hits the top of the screen, it kind of breaks off some of those colored blocks at the top. And that's why we call this game Breakout, because essentially you're trying to keep breaking out as many of those top pieces as possible. You lose the game when that ball passes the paddle, and that's when the game is finished. So you got to keep hitting the paddle up and up until you break out all of the balls. If you miss the ball, then you lose the game. So the Q function essentially tells us the expected total return that we can expect given a certain state and action pair. And the first point I want to convey to all of you is that it can be sometimes extremely challenging for even humans to define what is a good state and action pair, right? And what is a bad state and action pair. And I'm going to show two examples here. Out of these two examples, A and B, these are two examples of both states and actions. So you can see in state A, the action of the agent is to do nothing, right, as the ball is coming towards that agent, and it's going to bounce off the ball back towards the top of the board. Or state B, where the ball is coming towards the side, and the the agent is kind of out of the direction of the ball right now, but it can kind of zoom in at the last second and kind of hit the ball. Between these two state action pairs, which do you think will have the higher future expected return on rewards? Maybe enter your thoughts through the chat, and let's see what you guys think. So, and I just want to convey again that I think the first time I looked at this, I was really interested in the state action pair A, because this was a very conservative action to take. And I thought actually this would be the best action that could, or this would be the state action pair that would have a higher return on rewards. And we can actually look at a policy that behaves in the manner of this agent here. So now I'm going to play a video on the left-hand side, which actually shows kind of this strategy of the agent where it's constantly trying to get under the ball and hit the ball back up towards the middle of the screen. So let's watch this agent in practice. You can see it is successfully hitting off and breaking off balls, breaking off these colored boxes at the top of the screen. So it is winning the game, but it's doing so rather slowly, right? So it's kind of breaking off all of the points in the middle because its strategy is kind of conservative to hit the middle of the screen. Now let's consider strategy B by a different agent, where the agent may even potentially purposely move away from the ball just so it can come back and hit it from an angle. What does this agent look like? So here's an example where you can see the agent is really targeting the edges of the screen. Why? Because the second it attacks the edges, it's able to break off a ton of the balls from the top of the screen just by entering through a small door kind of that it creates in the side of the screen. So this is a very desirable policy for the model, but it's not a very intuitive policy that humans would think about necessarily, that you would need to attack those edges just for kind of unlocking this cheat code almost, where you can now start to kill all of the balls or blocks from the top of the screen. So we can now see that if we know the Q function, then we can directly use it to determine what is the best action that we should take at any moment in time or any state in our environment. Now the question is, how can we train a neural network or a deep learning model to learn that Q function, right? So we kind of have already answered the second part of this problem, given a Q function, how to take an action. But now we need to answer the first part of the problem, which is how do we even learn that Q function in the first place? Well, there's two different ways that we could do this. One way is an approach very similar to the formulation of the function itself. So the function takes as input a state and an action, and it outputs a value, right? So we can define a neural network to do exactly the same thing. We can define a neural network that takes as input convolutional layers with an image input that defines the state, just the pixels of our board or of our game at this moment in time. And also, simultaneously, we can feed in our action as well. The action that the agent should take at this given state, for example, move towards the right. Right? Now the output, we can train our neural network to just output this Q value. Okay, that's one option that we could use for training this system with a deep neural network. And I'll talk about the actual loss function in a little bit later, but first, I want to share also this idea of a different type of method. And I want to kind of debate a little bit which one you think might be better or more efficient. Now, instead of inputting both the state and the action, we're going to input only the state, and we're going to learn to output the Q value for all of the different possible actions. So imagine, again, we have a finite set of actions. We could have, let's say there are K actions. We could have our neural network output K different Q values, each one corresponding to taking action 1 through action K. Now, this is often much more convenient and efficient than the option shown on the left-hand side. Why is that? Because now, when we want to evaluate what is the best action, we only need to run our network once given a state. So we feed in our state, we extract all of the Q values at one time simultaneously, and then we just find the one with the maximum Q value, and that's the action that we want to take. Let's say we find that this Q value, Q of SA2, this is the highest one out of all of the K Q values. So this action, A2, is the one that we ultimately pick and move forward with at that state. Whereas if we're on the left-hand side, we have to feed in each action independently. So to find what is the best action, we'd have to run this neural network K times and propagate the information K times all the way over. So what happens if we take, first of all of the best actions? And the point I want to get at here is I want to start answering this question of how we can actually train this Q-valued network, right? And hopefully this is a question that all of you have kind of been posing in your minds thus far, because we've kind of talked about how to use the Q-value, how to kind of structure your neural network in terms of inputs and outputs to find the Q-value, but never we talked about how to actually train that neural network. So let's think about the best case scenario, right? How an agent would likely perform in the ideal case. What would happen if we took all of the best actions, okay? Well, this would mean that the target return would be maximized, right? And this can serve as our ground truth to train the agent, right? So to train the agent, we're going to follow this simple ideology, which is in order to maximize the target return, we're going to in order to train the agent, we will ultimately maximize our target return, right? So to do this, we're going to first formulate our expected return as if we were going to take all of the best actions from this point onwards, right? So we pick some action now, and then after that point, we pick all of the best actions. So think kind of optimistically, right? I'm going to take some action now, and then I'll take all of the best actions in the future. What would that look like, right? That would be my initial reward at time t that I get right now by taking this current action, right? So I take some action, and my environment immediately tells me what my reward is. So I can hold that in my memory as ground truth for my training data. And then I can select the action that maximizes the expected return for the next future scenario, right? And of course, we want to apply this discounting factor as well. So this is our target, right? So now let's start about thinking about estimating this prediction value, right? Q of SA. So this is the Q given our current state and action pair. That is the expected total return given our state and our action. And that is exactly what our network is going to predict for every one of our different actions. How can we use these two terms here to kind of formulate this loss function that will train our neural network and provide some objective that we can backpropagate through? So this is known as the Q loss. And this is how we can train deep neural networks, right? So we predict some value, right? So we pass our state and our actions through our network. We get some value. That's on the right side. That's the predicted value right here. And then our target value is just going to be obtained by observing what our reward was at time t. So we take that action, and we actually get a reward back from our environment. That's a tangible reward that we can hold in memory, and that's going to define our second part of the loss function. And then combine that with what we expect our expected total future return on rewards would be. And that's our target value. Now our loss function is just simply we want to minimize the divergence between these two. So we subtract them, we take some norm over them, like a mean squared error, and that's our Q loss. So we're going to try to have our predictions match as closely as possible to our ground truth. Okay, great. So now let's summarize this whole process, because I've kind of thrown a lot at you. Let's see how all of this kind of comes together and can shape up into a solid reinforcement learning algorithm that first tries to learn the Q function. So first, we're going to have our deep neural network that takes as input our state at time t. And it's going to output the Q values for, let's say, 3 different possible actions. In this case, there are 3 actions that our breakout agent can take. It can either go left, it can go right, or it can stay in the middle and take no action. Okay, so for each of these 3 actions, there's going to be one output. So we'll have 3 different outputs. Each output is going to correspond to the Q value, or the expected return of taking that action in this state. So here, for example, the actions are left, right, stay, and we can see that the Q values, for example, are 20 for left, 3 for stay, and 0 for right. And we can actually, this makes sense, right, because we can see that the ball is moving towards the left, the paddle is already a bit towards the right, so the paddle is definitely going to need to move towards the left, otherwise it has no chance of really hitting that ball back into place and continuing the game, right? So our neural network is able to output these 3 different Q values. We can compute our policy, which is what is the best action that we want to take in this given state, by simply looking at our 3 Q values, looking at which is the highest, right? So in this case, it's 20, which corresponds to the Q value of action number 1, which corresponds to the action of going left. And that's the action that our network should execute, or our agent should execute. So because that had the highest Q value, now our agent is going to step towards the left. Now, when that agent steps towards the left, that's an action that gets fed back to our environment, and our environment will respond with a new state. That new state will be, again, fed over to our deep neural network, and we'll start this process all over again. Now, DeepMind showed how these networks, which are called deep Q networks, could actually be applied to solving a variety of different types of Atari games, not just Breakout like we saw on the previous slide, but a whole host of different Atari games, just by providing the state, and oftentimes the state was in the form of pixels only. On kind of the left-hand side, you can see how these pixels are being provided to the network, passed through a series of convolutional layers like we learned about yesterday, and then extracting some two-dimensional features from these images of the current state, passing these to fully connected layers, and then extracting or predicting what our Q values should be for every single possible action that the agent could take at this moment in time. So here, for example, the agent has a bunch of different actions that it could execute, all on the right side, and the network is going to output the Q value for executing each of these different possible actions on the right. Now, they tested this on many, many games and showed that over 50% of the games, just by applying this kind of very intuitive algorithm where the agent is just stepping in the environment, trying out some actions, and then maximizing its own reward in that environment, they showed that this technique of reinforcement learning was able to surpass human-level performance just by training neural networks to accomplish and operate in this manner. Now, there were certain games that you can see on the right-hand side that were more challenging, but still, given how simple and kind of clean and elegant this algorithm was, it's actually, to me, still amazing that this works at all, right? Now, there are several downsides to Q learning, and I want to talk about those, and those will kind of motivate the next part of today's class. So the first downside is the complexity side, right? So in Q learning, our model we can only kind of model scenarios, right, that we can define the action space in discrete and small pieces, right? So and the reason for this is because we have to have our network output all of these actions as Q values, right? So our number of outputs has to be, number one, has to be fixed, right? Because we can't have our neural network output a variable number of outputs. And it has to be also relatively small. We can't have extremely large or infinite action spaces or continuous action spaces necessarily. And that's the other downside, right? So we can't easily handle, at least in this basic version of Q learning, handle continuous action spaces. There have been some updates of Q learning that now can handle continuous action spaces, but in the foundational version of Q learning, typically we can only handle discrete or fixed amounts of actions that an agent can tackle at any moment in time. The other side is the flexibility, right? So our policies are now determined deterministically by our Q function, right? So we have some Q function that are network outputs, and we simply pick the maximum, the action that has the maximum Q value, right? So that's a deterministic operation. It cannot learn, for example, stochastic processes where our environment is kind of stochastic, right, and may change different outcomes in the future. So to address both of these issues, actually, we're going to have now the second part of today's lecture, where we're going to consider a new class or a different class, rather, of reinforcement learning algorithms, which are called policy gradient methods. Now, just again as a recap, we already saw what value learning was, where we tried to first learn the Q function and then extract actions based on maximizing our Q function. Now, in policy learning, we're simply going to directly learn the policy that governs our action-taking steps, or our ideal action-taking steps. Now, if we have that policy function, that's a function that takes as input state and outputs an action, we can simply sample from that function, give it a state, and you will return an action. So essentially now, we want to, let's first revisit the Q function, the Q neural networks. These take as input a state, and the output a expected maximum reward or return that you can expect to have if you take this action, each of these actions. right? Now in policy learning, we're going to be not predicting the Q values, but we're going to directly optimize for pi of S. So our policy, its state S, which is the policy distribution, you can think of it, directly governing how the agent should operate and act when it sees itself placed in this state. So the outputs here give us the desired action in a significantly more direct way, right? So the outputs represent now not a expected reward that the agent can achieve in the future, but now it represents the probability that this is a good action that it should take in this state, right? So it's a much more direct way of thinking about this problem. For example, what's the probability that this action will give us the maximum reward? So if we can predict these probabilities, for example, here, let's say we train this policy gradient model, it inputs a state, and it outputs 3 different probabilities now. For example, the probability that going left is the best action is 90%, the probability that staying is 10%, and the probability of going right is 0. Right? We can aggregate them into pi to define what's called our policy function. And then to compute the action that we should take, we will sample from this policy function. Right? So keep in mind that now we see that our sample is action A, but this is a distribution. Right? This is defining a probability distribution. And every time we sample from our pi of S, our policy function, 90% of times we'll get action A, right, because our weight on action A is 90%, but 10% of times we'll also get a different action, right, and that's because this is a stochastic distribution. And again, because this is a distribution, all of the outputs of our neural network must add up to 1 here in order to maintain that this is a valid and well-formed probability, right? Now, what are some advantages of this type of formulation in comparison to Q-learning? Well, the first thing is that we can now handle continuous action spaces, not just situations where our actions are fixed and predefined. Maybe we can have a situation where instead of saying, OK, my actions are I go left, I go right, or I stay, that's it. Now, let's say I can have a continuous number or a continuous spectrum of actions, which is actually an infinite set of actions ranging from I want to go really, really fast to the right to really, really slow to the right, to really, really slow to the left, or really, really fast to the left, right? So it's this full spectrum of kind of speeds that you want to move in this axis. So instead of saying which direction should I move, which is a kind of a classification problem, now I want to say how fast should I move. Now when we plot the probability of our action space, the likelihood that any action in this action space is a good action or an action that will return positive rewards, when we plot that distribution, now we can see that it has some mass over the entire number line, right? Everywhere on the number line, it's going to have some mass, some probability, not just at a few specific points or discrete points that are kind of predefined categories. Now let's look at how we can actually model these continuous actions with policy gradient learning methods. So instead of predicting a probability that an action given all possible states, which is actually not possible if there's an infinite number of actions in a continuous space, let's assume that our output distribution now is a set of parameters that define some continuous distribution. Okay, so for example, instead of outputting the mass at an infinite number of places along our number line, let's define, or let's have our network output a mean and a variance that defines a normal distribution, which will describe how we have the mass all over the number line. So for example, in this image, we can see the paddle needs to move towards the left. So if we plot the distribution here, we can see that the density of this distribution that the network predicts, it has mean -1, right? And it has a variance of 0.5. And when we plot it, we can see, OK, it has a lot of mass on the side that's going fast to the left. And we can also see that now when we sample from this distribution, we get an action that we should travel left at a speed of 0.8, let's say, meters per second, or whatever the units may be, right? And again, every time that we sample from this, because this is a probability distribution, we might see a slightly different answer, right? And again, just like before, because this is a probability distribution, the same rules apply the mass underneath this entire density function has to integrate to 1, right? Because it's a continuous space, now we use integrals instead of discrete summations, but the story is still the same. Great, so now let's look at how policy gradients work in a kind of concrete example. So let's revisit firstly this reinforcement learning training loop, or kind of environment loop that we saw earlier in today's lecture. So let's think about how we could train, for example, in this toy problem, an autonomous vehicle to drive using reinforcement learning and policy gradient algorithms. So the agent here is a vehicle, right? So its goal is to drive as long as possible without crashing. The states that it has, the observations are coming from some camera, maybe other sensors like LiDAR, and so on. And it can take actions in the form of the steering wheel angle that it wants to execute. So it can decide the angle that the steering wheel should be turned to in order to achieve some reward, which is maximizing the distance traveled before it has to crash, for example. So now let's look at how we can train a policy gradient network in the context of self-driving cars as a complete example and kind of walk through this step by step. So first of all, we're going to start with our agent, right? So we start by placing our agent somewhere in the world, our environment, right? We initialize it. Now we run a policy. Now remember, our policy is defined by a neural network. It's outputting the actions that it should take at any moment in time. And because it's not really trained, this policy is going to crash pretty early on. But we're going to run it until it crashes. And when it crashes, we will now record all of the states, the actions, and the rewards that it took at each point in time leading up to that crash, right? So this is kind of our memory of what just happened in this situation that led up to the crash. Then we're going to look at the half of the state action rewards that came close to the crash, and we're going to, so those are all rewards that we can say kind of resulted in a low outcome or a bad outcome. It's a low reward state, right? So for all of those actions, let's decrease their probability of ever being executed again in those states, right? So let's try some other actions at those places. And for the actions here, close to the beginning part, or close to the part far away from our bad rewards, from our penalties, from our crash, let's try to increase the probability of those actions being repeated again in the future, right? So now, the next time we repeat this process, because we increase these good actions and we've decreased the bad actions, now we can see the same process again. We reinitialize the agent, we run it until completion, and we update this policy. And we can keep doing this over and over again, and you'll see that eventually the agent learns to perform better and better because it keeps trying to optimize all of these different actions that resulted in high returns and high rewards, and it minimized all of the actions that came very close to crashing, so it doesn't kind of repeat those actions again in the future. And eventually, it starts to kind of follow the lanes without crashing. And I mean, this is really incredible because, first of all, we never taught this algorithm anything about lanes, right? We never taught anything about roads. All we told it was when it crashed and when it survived, right? All we gave it was a reward signal about survival, and it was able to learn that in order to maximize its rewards, okay, probably it should detect the lanes, it should detect the other cars, for example, and we should try to avoid those types of crashes. Now, the remaining question that needs to be seen is how we can actually update our policy on every training iteration in order to accomplish this, right? So in order to decrease the probability of all of the bad actions and increase the probability of all of the good actions, how can we kind of construct our training algorithm to promote those good likelihoods and demote the bad likelihoods? Now, the part of this algorithm on the left-hand side that I'm talking about is steps 4 and 5, right? So these are the main kind of next pieces that I want to start to talk about. And I want to kind of start by saying, what is the big challenge, first of all, with this whole training loop? And before I get to that, let's say here first, when we want to think about kind of the loss function for training this type of model, for training policy gradients in practice, we'll dissect it, first of all, to kind of look at what pieces it's comprised of. So the loss function is going to be composed of two different terms. The first one is this log likelihood. Think of this almost as being like a probability or the likelihood that it should select a given action from a given state. This is the output of our policy. right? So this is, again, just to repeat it one more time, the likelihood that our agent thinks that it should execute action A, given that it's in state S. We put that inside a log, so it's a log probability, and that's it, right? Now we multiply this by the total discounted reward that was achieved at this time t, right? Now let's assume that we got a lot of reward at this time, a lot of return by taking this action that had a high log likelihood. This loss will be very, very large, right? And it will reinforce those actions because they resulted in very good returns, right? On the other hand, if we had rewards that are very low for a specific action, so those are bad rewards or kind of penalties, right? Then those actions should not be sampled again in the future because it did not result in a desirable action. So we'd want to, in order to minimize our loss function, we'd want to minimize the log probability, the probability of sampling that action again in the future. That would essentially be equivalent to minimizing the probability of mass at that specific action state, given that point or that observation in the environment. And when we plug this into our gradient descent algorithm to train our neural network, we can actually see that policy gradients kind of highlighted here in blue, right? And this is where this method kind of gets its name from, right? Because when you take the gradient and you plug it into your gradient descent optimizer, the gradient that you're actually taking over is the gradient of your policy multiplied by the returns, right? And that's kind of where the connection comes into play a little bit. Now, I want to talk a little bit, as I conclude and wrap up this lecture, is how we can extend this framework of reinforcement learning into real life, right? So in the beginning, we talked a lot about gameplay and how reinforcement learning is really amazing, shown to do amazing things in games where we have kind of like a full observation of our environment. But in the real world, we don't have a full observation of our environment. Oftentimes, we don't even really know what's going to happen next a lot of time. In a lot of games, if I move my piece here, there is a fixed number of possible outcomes that can be shown back to me, right? So I have some level of understanding of my future, even if it's at one state. There's a fixed number of possible states in games often. Whereas in real life, that's very much not the case. Now, we can get around this somewhat by training in simulation, but then the problem is that modern simulators often do not accurately really depict the real world, and they do not really transfer to reality either because of that when you deploy them. So one interesting point here is, where does this whole thing break down, right? So if we want to execute this algorithm on the left, the key step that is going to break everything is step number 2 if we try to do this in reality. Why? Because in reality, we can't just go out and crash our vehicles and let them drive on roads and just crash just so that we can teach them how not to crash, right? So that's not the way that we can train, let's say, an autonomous vehicle to operate in reality. That's why simulators do come into play a little bit. And one cool result that we actually created in our lab was actually how we have been developing a brand new or photorealistic simulation engine for self-driving cars that is entirely data-driven. So it overcomes this boundary of this gap and this transferability of whatever we learn in simulation cannot be applied to reality. Now, because of this extremely photorealistic simulation that is entirely data-driven, the simulator is actually amenable to learning reinforcement learning policies and helping us use real data of the world to actually generate and synthesize brand new real data that is very photorealistic and allows us to train reinforcement learning in simulation and still be transferred and deployed into reality. So in fact, we did exactly this, and we showed that you can place agents within your simulator, within this simulator, train them using policy gradients, the exact same algorithm that you learned about in today's lecture. And all of the training was done entirely within the simulator called Vista. And then we took these policies and actually put them directly on board our full-scale autonomous vehicle on real roads, right? And there was a direct transferability of all of the policies that came over. And this represented actually the first time ever that a full-scale autonomous vehicle was capable of being trained using only reinforcement learning. There was no human supervision, and it was trained entirely in simulation and then deployed directly into reality. So that's a really awesome result. And actually in Lab 3, we're going to, all of you will have the ability to kind of, number one, play around with the simulator. Number two, train your own agents using policy gradients or whatever reinforcement learning algorithm you would like to train within simulation and design your own autonomous vehicle controllers. And then, kind of as part of the prizes, the winners will invite you to put your policies on board the car, and you can actually say that you trained an entire autonomous vehicle end-to-end using a single neural network and put your neural network onto the car and how to drive in real roads. So I think that's a pretty awesome result that should motivate all of you. So now we've covered the fundamentals behind value learning, policy learning, and policy gradient approaches. Very briefly, I'm going to talk about some very exciting advances and applications that we're seeing all over the world, right? So first, we turn to the game of Go, where reinforcement learning agents were put to the test against kind of human champions and achieved what at the time was an extremely exciting result. So just very briefly, a quick introduction to the game of Go. This is a 19 by 19 grid, extremely high dimensional in terms of gameplay. It's played between two players, white and black, and the objective of the game is to actually occupy more territory than your opponent. Okay, so the problem of Go, or the game of Go, is actually extremely complex. And in fact, the full size of the board, with this 19 by 19 board, there are a greater number of legal board positions than atoms in the entire universe. That's 2 times 10 to the 170 positions. Now, the objective here is to train an AI algorithm using reinforcement learning to master the game of Go, not only to beat the existing gold standard software, but also to beat the current world champion. So Google DeepMind rose to this challenge. A couple of years ago, they developed a reinforcement learning-based platform that defeated the grand champion of Go. And the idea at its core was actually very clean and elegant. So first, they trained the neural network to watch human expert Go players and learn how to imitate their behaviors. Then they used pre-trained networks to play against a reinforcement learning policy network, which actually allowed that policy to go beyond what the human experts had done in the past, but actually achieves what's called superhuman performance, right? And one of the tricks that really brought this algorithm to life and really to the next level was the use of an auxiliary network which took as input the states of the board and predicted how good of a state was that position. And given that network, this AI was kind of able to hallucinate almost how it could reach these great board positions and the steps it would have to take to reach these great board positions, and use those as actions essentially to guide its predicted values. And finally, in recently published research of these approaches, just over about a year or a year and a half ago, called AlphaZero, that only uses self-play and generalizes to 3 famous board games starting from chess to shogi and Go. And in all of these examples, the authors demonstrated that it was not only kind of possible to learn how to really master the game, but again, to surpass human performance and surpass at the time, the gold standard humans. So now just to wrap up today's lecture, I'm going to just to wrap up today's lecture, we talked about first the foundations of reinforcement learning in the beginning, kind of what defines a reinforcement learning environment, ranging from the agent to the environment to how they interact with each other. Then we talked about 2 different approaches for solving this reinforcement learning problem. First, with Q-learning, where we want to estimate using a neural network the total future expected return on rewards. And then later with policy gradients and how we can train a network to directly optimize our policies directly, and how we can actually extend these to continuous action spaces, for example, autonomous driving. Right, so yeah, so in the next lecture, we're going to hear from Ava on kind of the new, exciting, and recent advances of deep learning literature in the field, and also some kind of interesting limitations about what you've been learning as part of this class, and hopefully that can spark some motivation for you in the future of how you can kind of build on everything that you learned in this class and advance the field even further, because there's still so much to be done. So in a few minutes, we'll hear from Ava on that. Thank you very much.